Hey everyone, if you've been enjoying my free math lessons on Prodigy Mathematics, I've got a great way you can support the channel and supercharge your learning. I've launched Martian Mathematics, a growing collection of problem sets, quizzes, and fully worked out solutions designed to complement my videos. These aren't just generic worksheets. Each set follows my lesson structure, reinforcing key concepts with carefully crafted problems and step-by-step solutions. Every purchase helps keep this channel running, so I can continue bringing you high-quality, free math education. Check out Martian Mathematics on Teachers Pay Teachers today. Your support makes all the difference. And don't forget to like and subscribe. Lecture 7, Graph Sketching. So what exactly do I mean by that? Well, from algebra, you're used to plotting graphs. You may have done some sketching, but certainly the traditional approach is to plot graphs. So we would make a table of values. We might say x, and then have y equals, let's say, x squared plus 3x plus 2. We can make a table of values here. Maybe we'll look at minus 3, minus 2, minus 1, and 0, which would get value for minus 3, we'd get 2. For minus 2, we would get 0. Also for minus 1, we'd get 0 again. And then for 0, we would get 2. And then we might draw a Cartesian coordinate system. Minus 1, minus 2, minus 3, 1, 2. And we put these points on there. So at minus 3, we had 2. So we put that point there. And then also at 0, we had 2. So we put that point there. And then at minus 2 and minus 1, we had 0. So that would be right there on the x-axis. And so we'd look at that and we'd be like, okay, well, that's a start. We might then add to this table, putting more points in, until eventually we got something that was good enough that we might be able to sketch this graph. Something like that. Something like that. And that, of course, is point plotting. Right? We create a table of values and we plot each of those points on a Cartesian coordinate system. So what we're going to do today is a little bit different. We're going to use the tools of calculus to help us generate features. For example, is there a minimum? So this is a minimum value, at least locally. Yeah. Right? Or is it a maximum? Is it, we have two terms we'll talk about, concave up and concave down. So concave up, it's like a bowl facing up. Concave down is like a hat, right? And so we'll be able to get this information using calculus to add to our our repertoire of tools that we can use in sketching graphs. So we won't have to plot so many points. Well, we'll need a few theorems and definitions before we can really start. The first theorem is called the extreme value theorem. The extreme value theorem says if a function f is continuous on a closed interval, a, b, then f attains both an absolute maximum and an absolute minimum on that interval. These extrema occur either at a critical point in the open interval a, b, or at an endpoint a or b. Interestingly, that is a very difficult proof, so I'm not going to prove it. I don't think I'll show any proofs today, in fact. But it's the kind of proof that you're going to do in a more advanced calculus course like real analysis. The general idea is like this, though. Imagine that we had an interval, say from an open interval, let's say, from 0 to 1. And we're looking at the function y equals x. And let's pretend that we're like a computer. So we're just plotting a bunch of values, f of 0.1, f of 0.2, etc., etc. And we see that after we plot a significant number of these points and collect them in a table, that everything seems to be above a certain value and everything seems to be below a certain value. Now in this case, everything seems to be above 0, but less than 1. Now the limit, say, as x goes to 1 of this function is obviously 1. The extreme value theorem guarantees that that limit is in the interval, provided that it's closed. That's why we have to close the interval. Turns out this is at the endpoint. If we just consider the open interval from 0 to 1, then both the limit as x approaches 0 and the limit as x approaches 1, which is 0 and 1, are not in the set of values that we've plotted or collected, right? So but with a closed interval, then you get that. Okay, so the minima or maxima can occur at the endpoints, or they can occur in the open interval in between the endpoints. So let's get a couple of definitions. So I think it's well understood what it means for a value to be a maximum or a minimum. That means that every other value, so f of x, right, every other value of x is less than or equal to that maximum, right? And a minimum value would be f of x is greater than or equal to that minimum. So that's a maximum and a minimum value. Now, typically we'd say an absolute maximum or absolute minimum. That's when we're talking about the closed interval. If we're talking about an open interval, though, we could have what we call local maxima and minima. Okay, so for example, just the idea is that, let's say we had a rather complicated looking function. You see this has more than one maxima, yes? Yeah. So if the interval is here to here, then this is obviously a global maximum on that interval. Yeah. But this is a local maxima, which means that if we can construct an open interval around this critical point, which I'll define momentarily, we would find that this is in fact a maxima around, on some open interval that we can define. So that's a local maxima or minima. So when I use these terms, though, absolute maxima, minima, you should think over the whole interval, including the endpoints. Local maxima and minima, you should think of it as I could pick an open interval such that this value or this point was a maxima or a minima. So I mentioned the term critical number or critical point. So a critical number is a number c in the domain of a function f, and it's called a critical number if either its derivative f prime evaluated c is equal to 0, or if f prime of c does not exist. We have one more theorem that's going to be really useful for us, and that's Fermat's theorem. Fermat's theorem says that if f has a local maximum or minimum at c, and f is differentiable at c, then f prime of c is equal to 0. When when the derivative is equal to 0, we usually call that a stationary point. So critical points can be either stationary points or points where the derivative does not exist. So what would that look like graphically? Well, a stationary point would be, if this is my function, it's got some maxima here. If we look at the derivative at this point c, which I'll put right here, right, we'll call this point c on our axis. What does the slope look like up here? Well, the slope looks like a horizontal line, which has a slope of 0. So the derivative is 0 there, you see? Yeah. But you could also have a critical point if maybe the function looked like this. And I'll just put a little, yeah. So the derivative doesn't exist at this point, c in this case, because the derivative from the left is not equal to the derivative from the right, right? They're opposite signs. And so this would be a point where the derivative is not defined at c, but it could represent a critical point or a critical number. I think when we do an example, it will make more sense. So let's consider the function f of x equals x minus 3 quantity squared minus 2x on the closed interval 0 to 8. So along the way here, I'm going to ask the viewers to pause the video and evaluate things along the way, just to get some practice at this. So the first thing that we're going to need to do, right, is we're going to utilize Fermat's theorem and see if we can find any critical points. So go ahead and pause the video, take the derivative of this function, and come back when you've got your answer. Okay, so the derivative, f prime of x, is going to be equal to 2. X minus 3, the derivative inside here is just 1, minus 2. And so Fermat's theorem tells us that if there is a maxima or a minimum, if there is a maxima or a minima on this interval, on the open interval 0 to 8, then we should expect that the derivative equals 0 at that critical point, okay? So we can set f prime of x equal to 0. What does this mean? This means that 2 times x minus 3 minus 2 is equal to 0. Which really says we can divide out the 2. That's going to give me x minus 3 equals 1, which means that x is equal to 4. So at x equals 4, the derivative is in fact equal to 0, which makes it a potential critical point where there could be a maximum or minimum value. But we now need to evaluate the function at all the critical points that we found. We've only found 1, 4, and at the endpoints, 0 and 8. So let's evaluate those. So let's do 0 first. F at 0, well, if this is 0, then this is minus 3 squared, which is 9 minus 0, so that's equal to 9. And then let's evaluate it at the point x equals 4. That was a critical point. F of 4 would be equal to, well, 4 minus 3 is 1, and 1 squared is just 1. And so we have 1 minus 2 times 4. That's 1 minus 8 is minus 7. And then f at 8, plugging 8 in here, 8 minus 3 is 5. 5 squared is 25. minus 2 times 5, that's 10. So what is 25? Oh, sorry, 8. X is 8. So 2 minus 8 is 16. So I have 25 minus 16 is 9. And so these are the points that we found on the endpoints and also at the critical point. And so we see that on this interval, we have a maximum of 9. So the max is equal to 9. And it occurs at x equals 0 and x equals 8. The min is minus 7, and that occurs at x equals 4. And so if I show you what this graph looks like, this is what it looks like. We see that minimum occurring right here at x equals 4, has a minimum value of minus 7, and the maximum on these intervals are at the endpoints, 0 and 8, and they have a value of 9. Let me point out that when reading questions and homework and on quizzes that ask for a maximum, don't read the problem carefully, because sometimes you may be asking for what the maximum is. Sometimes the question may be asking where the maximum or minima occurs. So in the problem that we just did, the maximum value was 9, and it occurred at 0 and 8. So if you said the maximum is 0 and 8, that's not correct. The maximum is actually 9, and it occurs at 0 and 8.
Yeah.
Okay? So read the questions carefully so you don't make that simple mistake. So let's characterize in terms of the slope or the derivative what an increasing and a decreasing function looks like. So if I have an increasing function, what does that look like? That means it's increasing somehow, right? Does everyone agree that that looks like it's increasing?
Yeah.
You know, imagine your Cartesian grid down here. As x is going this way. So as x is increasing, the value y is increasing, you see?
Yes.
So if we look at the slope, let's put some tangent lines along the way here. So here we might have a tangent line. Here we might have a tangent line. Here we might have a tangent line. See that?
Yeah.
Each of these tangent lines, is the slope of these tangent lines positive or negative? Yes, they're positive. That's right. So what characterizes an increasing function is that the derivative of the function is greater than 0. What about a decreasing function? Well, this might look like a decreasing function, right? Something like that. So if I draw tangent lines on this, might get a tangent line here, tangent line here, tangent line here. Those are not very tangential. I know they're not touching, but you see the idea. Now what about the slope of these tangent lines? Are they positive or negative?
Those are negative.
They're negative slopes. They're like going down, right? So this is an increasing function. This is a decreasing function. And we see that the slope, or the derivative, will be characterized by values that are less than 0. Does that make sense?
Yeah.
Yeah? So this is the basis of what we call the first derivative test. The first derivative test says, suppose f is continuous near c and differentiable except possibly at c, and that f prime of c is equal to 0. Well, if f prime changes from positive to negative at c, then f has a local maximum at c. If f prime changes from negative to positive at c, then f has a local minimum at c. If f prime does not change sign at c, then f has no local extremum at c. See, what is that saying in pictures? Well, if we have a local maximum, let's say, we can imagine the tangent lines, right? What do they look like? They're positive over here. At the very top, that tangent line has a slope of 0, and then it changes sign and it goes to be negative. So if I were to plot f prime of x and evaluate at various points, let's say at minus infinity, out to the point C, which is this point here, and then out to positive infinity, I can see that everywhere to the left in this region, we have a positive slope. So we have little plus marks like this. Well, actually, I wanted to do this. Let me put the C a little lower here. At the point C, the slope, of course, is 0. That was part of the theorem, right? That we had a point C where it's f prime of C was equal to 0. And then over here, the slope becomes negative. And so when we see that kind of behavior, where we go from a positive slope to a negative slope with 0 in between, obviously it's continuous, so it needs to be like that, then this would represent a local maximum. Okay? Similarly, for a local minimum, what would that look like? Well, let's draw something that looks like a minimum. We've got slopes, tangent lines. down here. So f prime of x minus infinity to infinity. Critical point C here. What do the values look like? Well, here we see negative slopes. So negative, 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 negative. At the critical point, it's 0. And then it switches to positive slopes, you see? So this is a local minimum. So this is the picture that we're looking at. This little kind of mini graph, they have a name for these things. I forget what they're called. But where you draw something along these lines with these pluses and minuses where the critical points are marked on it. This can be a guide to tell us whether we have a maximum or a minimum. So let me do an example. Again, we're going to need to evaluate the derivative of this function, x cubed minus 3/2 x squared, in order to find critical points. And so I invite the viewers at home to pause the video, try taking that derivative now, come back when you have your answer. So let's take a derivative. F prime of x will be equal to 3x squared minus, we'll have 3/2 times 2x. You can see the 2's are going to cancel here, and so that will give us 3 times, actually let's factor out an x out of this as well. 3x times x minus 1. There, that's our derivative. And of course, to look for critical points, we're looking for places where f prime of x is equal to 0. So that means that 3x times x minus 1 is equal to 0. Well, where could that be, right? That could be at x equals 0, and that could be at x equals 1. Yes?
Yeah.
So we've got two potential critical points, x equals 0 and x equals 1. So what I want to do now is I want to make one of these graphs showing how the sign, showing the intervals where the slope is increasing and decreasing for the function f. And so I'll write it like this, f prime of x. You can see the domain of this function is pretty much over all the real numbers, so minus infinity to infinity. Typically, I don't know, are you guys familiar with this notation? The domain is all the reals. Make these funny looking double barred lines.
I've not seen it before.
That means real numbers. So if I write that down, that means the domain is all the real numbers. And so we'll evaluate going from minus infinity, and we need to put in our critical points. We have a critical point at 0 and another one at 1. So I'll put a 0 and then a 1, and then let's go on out to plus infinity. At 0 and 1, the derivative evaluates to 0, right? That's what we just determined here. So we'll put 0 here. You have to be careful when doing this because sometimes we want to plug values into f of x. Like in the previous examples, we were finding maxima and minima on an interval, right? And sometimes we want to plug values into the derivative. So we have to be careful. Here we're concerned about values for the derivative. We want to see where it's increasing, where it's decreasing. So we want to see what the sign of it is so we can determine whether f of x is increasing or decreasing in that interval. So we need a test number, right? So we want to pick a number that's to the left of 0. Let's just choose minus 1 because that's easy, right? So we plug minus 1 into 3x times x minus 1. What are we going to get? Well, we've got minus 3, so we'll do f prime of minus 1 is equal to, we're going to get minus 3 times minus 1 is minus 2, right? Which is equal to a positive 6. So that is a positive value. So we can see that everything to the left of 0 will be a positive value. Now we need to pick a test number in between 0 and 1. So we'll pick a half. So we'll try f prime of 1/2. And that's going to be equal to, we have 3/2 times 1/2 minus 1. What is 1/2 minus 1? That's the same thing as minus a half, right? And we don't even need to get the actual number. We just need to see that it's negative, you see? So it's negative, which means all the other values in between 0 and 1 will be negative. So put negatives here. And then we'll need to look for things in the region to the right of the value 1. So we'll pick f of 2. So 3 times 2 is 6, and 2 minus 1 is 1. And so we can see that's positive again, right? Positive, 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 positive. And so what does this information tell us? Well, at 0, it appears that we have a maxima, right? Because we went from a positive slope to 0 to a negative slope. That is tracing out the tangent lines on a maximum value in this original function. But here at 1, what do we have? We have a minimum value because we're going from negative slopes to 0 and then back to positive again. So you can see that's kind of traced out a minimum value, right? So something like this is going on, you see?
Yeah.
Got a maximum and then a minimum. And so if I were to show you a graph of this function, you would see that that is the case. We first have a maximum value. That's where it's going from positive slope to negative slope. And then we have a minimum value, which is where it's going from a negative slopes to positive slopes again.
Yeah.
Okay? We'll actually return to this function in a minute. But first I want to talk about the second derivative test. First, a couple of definitions, though. So, concave up is basically a curve that looks like that. Looks like a cup, okay? Whereas concave down looks like a hat. Think of it as the cave pointing up or as the cave pointing down, right? So concave up, concave down. And so when we characterize Extrema based on its concavity, that's the term we use, concavity. Right? That means, is it concave up, is it concave down? As a test function to see how this works, let's consider the parabola y equals x squared, right? Obviously it's concave up, yes?
Yeah.
Now if I take a derivative of this, what is the derivative, right? So y prime is equal to 2x, yes? If I graph that, it looks like a line, right?
Yes.
Well, what if I take the derivative of y prime? So I take the derivative of 2x. What's the derivative of 2x?
2.
2. And the way we write that, I hope you remember, is y double prime equals 2. That just means that I took a derivative of y equals x squared twice. Call it the second derivative. I'm pretty sure we had it in our homework, but we haven't really talked about it very much. What does that graph look like? Well, it's obviously just the positive number, positive 2, right? It's a horizontal line, its value is 2. Now let's look at a different graph. Let's look at y equals minus x squared. What does minus x squared look like? It looks like this, right? Just like x squared, except everything goes down, right?
Yeah.
If I took the derivative of this, what would I get? I'd get y prime equals minus 2x. And if I took a second derivative, I would get, and that would look like, of course, a negatively sloped line, yes?
Yes.
And if I took a derivative of this, I would get y double prime is equal to minus 2. This is kind of a, in pictures, explanation of what's called the second derivative test. The second derivative test says, suppose f prime of c is equal to 0, and f double prime is continuous near c. If f prime of c is greater than 0, then f has a local minimum at c. If f double prime is less than 0, then f has a local maximum at c.
All right.
If f double prime of c equals 0, the test is inconclusive. But on the matter of if f double prime is equal to 0, a point x equals c is an inflection point of f. If the concavity of f changes at c, that is, if f double prime of x changes sign at x equals c, and f is continuous at c. So we can look for potential inflection points, and we'll see one in just a moment, by looking for places where the second derivative is equal to 0. But we have to test to the left and to the right of that to see if it does in fact change signs, if the second derivative changes signs. So that means going from concave up to concave down, or concave down to concave up. So we're going to revisit the example we just did. Okay, so I've just put up the results that we had from before. I guess we could note that we had some critical numbers, x equals 0 and x equals 1. Now let's take a second derivative, which means we just need to take the derivative of this. I'm going to go ahead and expand this out. That'll make it a little easier for taking derivatives. That'll give me 3x squared minus 3x. So actually, this would be a good opportunity for viewers at home to practice their differentiation. So go ahead and pause the video. Take the second derivative of f of x equals x cubed minus 3 halves x squared, and come back when you have your answer. Okay, so all we really need to do is just take another derivative of 3x squared minus 3x, because that is the first derivative of our original function. So let's take a derivative of that. We'll get that f double prime x is equal to, give me 3 times 2 is 6x minus 3. The first thing we want to do is look for an inflection point. And so we want to look for an inflection point by looking for places where the second derivative is equal to 0. And so that means that 6x minus 3 equals 0, which of course means that x is equal to 1/2, right? 1/2. Now let's look at what the second derivative is doing. First, I'm going to put back up what we had for the first derivative, the graph. Okay, this is what we had found for the first derivative around these critical points 0 and 1. Now I want to look at the second derivative. And you want to try to line up your two graphs. So the point of interest for the second derivative is at this potential inflection point at x equals 1/2. So I'm going to put that in between 0 and 1 here, 1/2. And then we'll go back out to infinity. And so if we ask, what does this function look like for x less than 1/2, like pick something like 0. Well, at 0, f double prime of 0 is equal to minus 3. So it looks like the values are negative. We'll put 0 here for this inflection point, or possible inflection point. Now we need to look at what the values are to the right of 0. So we'll pick another value, like say 1. So we'll do f of 1. And that is equal to, that's 6 minus 3 is 3. That's positive. So you can see that the point x equals 1/2 is in fact an inflection point, because that's where it goes from concave down to concave up.
Yeah.
Okay?
All right.
Also, you can use the second derivative to evaluate the concavity of these critical points. So if I look at f prime of 0, or excuse me, f double prime of 0, so I'll evaluate right here, f double prime of 0 is equal to minus 3. That's negative, which makes this concave down, making that a maximum. Evaluate the second derivative at the critical point. Remember, the critical point comes from the first derivative. But we can evaluate the second derivative at that point, f of 1. That's going to give me 3, which is positive, which tells me that this is concave up. Well, really what it's telling you is that this is a minimum, right? So because the second derivative is greater than 0 at that point, that makes this point a local minimum. Because the second derivative at 0 is negative, that makes this a local maximum by the second derivative test. So the first derivative test allows us to find intervals of increase and decrease, which helps us pinpoint maxima and local maxima and minima. But we can also use the second derivative test to verify, if we want, that that's the case.
All right.
Is everybody following this so far? Okay, so let's put these tools to use and sketch graphs. And so I'll lay out a general procedure for how to do this. And so it's like a 7-point plan, if you will. So to sketch the graph of a function f of x, follow these steps. Number 1, determine the domain of f. Number 2, check for symmetry, even, odd. There are other symmetries, like oblique symmetry, that might come into play. Step 3, find the x and y intercepts. Now, once we find the x and y intercept, we'll want to plot those points on our graph. Step 4, identify any asymptotes. Remember, vertical asymptotes are where f is undefined and the limit is plus or minus infinity. And horizontal asymptotes are based on the limits going out to x equals plus and minus infinity. So what does it look like in, over a great distance, right? Usually that comes into play for rational functions. Step 5, find critical points using the first derivative test. Step 6, determine the concavity and inflection points using f double prime, using the second derivative test. And then combine all this information to sketch the graph. So let's do an example. Okay, so I'll work this example. Our function is f of x equals the quantity x squared minus 2x plus 4 divided by x minus 2. Step 1 is to determine the domain of this function. We could write the domain in several different ways, but basically you see it's defined everywhere except at x equals 2. What goes wrong at x equals 2?
It's over 0.
Yeah, it's divided by 0. 2, check for symmetry. So is it even or odd? Well, do you remember how to tell if a function is even or odd? the definition of an even function is one where f of minus x is equal to f of x. That's an even function. An odd function is where f of minus x is equal to minus f of x. That's an odd function. So if we plug in minus x for x here, we see that this will stay positive, this will flip signs, this will stay positive, and this will flip signs. And so that is, in fact, because if everybody flipped the same, then we could be equal to minus f of x, and that would be odd. But it doesn't, so it's neither even nor odd. So there's no symmetry really here to take advantage of. By the way, if you do find symmetry, it means you only have to work on half the problem, right? You can focus on one side of the problem because the other side will have this symmetrical relationship. Or step 3, find the intercepts, the x and y intercepts. Well, we find the x-intercepts by looking at f of x equals 0, which means that we're going to have to factor this. So we need to factor x squared minus 2x plus 4. And you can do this in numerous ways. You can use the quadratic formula. You can complete the square. I think we'll just complete the square. I'll show it to you in case you've forgotten. I'm going to rewrite this as x squared minus 2x plus minus 1 squared minus minus 1 squared plus 4 equals 0. So this part here just pulls into x minus 1 squared. And this part over here, this becomes minus 1 squared is just 1 plus 4. So that's just going to be 3. And that means that we have x minus 1 squared equals minus 3. And we can see where that's going, because as soon as we take a square root, what's going to happen? Well, it's going to be imaginary, right? It means there are no real roots, which means it doesn't cross the x-axis anywhere. So there are no x-intercepts. So I'll make a note of that. We've got no x-intercepts. What about y-intercepts? That's where f of 0, right? So if we evaluate f of 0, what do we get? We're going to get 0 minus 0. We're going to get 4 over minus 2. That's just minus 2. So our y-intercept, minus 2. So we've got 1 point to put on our graph so far. If I put my graph over here, I have 1 point to put on here, and that is at x equals 0 and at minus 2. All right, step 4 asks us to identify any asymptotes. Obviously, we have a vertical asymptote at x equals 2. And so I'm going to go ahead and label that 1, 2. I'm going to just put a dotted line. I'll maybe even put a colored dotted line just to make it a little easier to see. There we go. That's our vertical asymptote. What about horizontal asymptotes? Well, typically the way that you do this, right, is you take the highest order terms from the numerator and the denominator, and you see where that goes, right? And so you can see that this is going to go in the limit when you're far away at minus infinity or positive infinity. This is going to look like x. You know, if you don't see that immediately, right, you can just throw away the minus 2. You can throw away the minus 2x plus 4, because when x is very big, those are irrelevant. And so I'm left with x squared over x, which looks like x. Alternatively, you can divide x minus 2 into x squared minus 2x plus 4. Right? You're going to get x plus 4 over x minus 2, right?
Yeah.
Which in the limit, when x is very large, is going to look just like x. So we call this, I'll put it here, oblique asymptote. And I'm going to draw that in. It's just the line y equals x. I guess I should write y equals x. So I'll go ahead and draw that in. Yeah, looks something like that. 5, find the critical point. So now we have to take a derivative. And in fact, I think this would be a good place to give the viewers an opportunity to practice their calculus skills. Go ahead and pause the video. Take a derivative of f of x equals the quantity x squared minus 2x plus 4 divided by x minus 2. When you get your solution, come back and I'll show you how it's done. Okay, so this could be a little messy. Let's see, f prime of x. Well, we're going to have to use the quotient rule, Hody high. So we'll get x minus 2 times the derivative of the numerator. That's going to be 2x minus 2 minus hidey ho, which will give us x squared minus 2x plus 4 times the derivative of the denominator is just 1. So we can write that like that. All divided by ho squared, so that's x minus 2 squared. Let's go ahead and multiply through over here. That's going to give me 2x squared minus 2x minus 4x plus 4. And then we'll go ahead and subtract this off over here. Minus x squared plus 2x minus 4 over x minus 2 squared. And so we see there's a lot of cancellation going on here, right? This positive plus 2x will cancel this minus 2x here. This plus 4 will be canceled with this minus 4 here. X squared and 2x squared, that's going to give me, I'm just going to write my solution here. Got to cancel that out. That goes away. I'm just left with 2x squared minus x squared is just x squared minus 4x over x minus 2 squared. But look what we can do here, right? We can factor out an x minus 4. I thought we'd have some cancellation, but we don't. Okay, there. So that's what we get in the end. Let me make that a little neater. X times x minus 4 divided by x minus 2 squared. We need to look for critical points. Well, critical points occur where? Where f prime of x is equal to 0. Well, we can see where that's going to happen, right? That's going to happen at x equals 0 and x equals 4. Yes?
Yeah.
But also where f prime of x is not defined. Well, that happens at x equals 2. But x equals 2 is not in the domain. Okay, so this would count as a critical point if x equals 2 was in the domain, but it's not. So it's not actually a critical point. So really our critical points are here. Maybe we'll keep the 2 around just to check it. And of course we can use this to find out where the intervals of increase and decrease are. So we'll go out here from minus infinity to the point 0. I'm going to put the point 2 in anyways, just to make sure there's no funny business going on there, but it's not a critical point. I'm listing it anyways. And then the point 4. And then of course we go back out to infinity again. Got to pick a test function here for this interval between minus infinity and 0. Let's pick something like f prime of minus 1. And what's that going to give us? It's going to give us a positive 5/9. We plug in minus 1 here. So here we've got positive. At 0, of course, we're equal to 0. And the same thing with that 4. That's where our critical, those are the 2 stationary points that we found. Now let's evaluate in between 0 and 2. That's why I kept the 2 around. I just want to check in between both of them, make sure it doesn't change sign. So we'll pick 1 here, f of 1, or f prime of 1 rather. So what do we get then? We get minus 3. Yeah, it's negative. So we get negative values here. Let's just double check and let's look at 3, right? If we put in f prime of 3, is it going to be positive or negative? Well, we get 3 minus 4 is minus 1 times a positive number divided by a positive number is negative. So it stays negative. So we can stop worrying about 2. I'll go ahead and erase that. And then finally, let's look out here at beyond 4. What do we get? So if we look at, say, f prime of 5, so a little test point. 5 minus 4 is positive 1 times 5 is also a positive number divided by a positive number is positive. So it's positive. So what does that tell us about this graph so far? It's telling us that looks like we've got, what does this look like? We're going from a positive slope to a negative slope. That looks like a maximum to me, right? Maximum. And then we're going from negative slope to a positive slope. That looks like a minimum. Okay, but don't be so, that's why we drew the asymptotes. We can't just throw down, one of those. That's not going to work because that's going to cross these asymptotes, yes?
Yeah.
So we cannot be so hasty. You can do, I'm not going to do it, it would just take far too long, but you can do a second derivative test on this, okay? So if I want to find out what f double prime of x is, I have to take the derivative of this, right, which is a combination of product rule, quotient rule, or you could just multiply them through like here. And you have another quotient rule problem, and when you do that, you should get 8 over x minus 2 cubed, for which you can see that there is no point at which that can be equal to 0, so there is no inflection point, because 8 can't be equal to 0, right? You can use this function, however, to verify whether this is a maximum or not. You can plug in for f double prime of 0. If it is a maximum, what value do we expect for the second derivative? Negative, right? So that's what our second derivative test tells us. So if we plug that in using this formula here, we get 0 minus 2 is just minus 2, and minus 2 cubed is a negative number. So this is negative. And then if we plug in for 4, right, f double prime of 4, we get 4 minus 2 is 2, but that's a positive 2. 8 divided by a positive number is still positive, so this is positive, and so we see that this does confirm that this is a minimum. local minimum. There's no inflection point, so that means a curve like this is out of the question because this is an inflection point where it goes from concave down to concave up. We don't have a graph like that here. So let's put some points on that we know. Let's put our critical points on. So what is f of 0? Remember, this is f of 0, not f prime of 0 or f double prime of 0. Well, f of 0 would be, well, we've got 0 minus 0 is 4 over minus 2. That's equal to minus 2. Let's also evaluate what it is at x equals 4. So f of 4, plug in 4, that's going to give us 16 minus 8 plus 4 over 4 minus 2 is 2. So that's 16 minus 4 is 12 over 2. It should be 6. Let's go ahead and put these points in. Okay, so we have 0 and minus 2. We already have that point labeled right there, but we know this is a maximum. Okay, so we're going to have some kind of curve that maxes out here, right? So I'm just going to draw something in temporarily. We know it's going to be a maximum, so I need to make something that looks like a maximum. I need to draw it as concave down. And then over here at 4, 6, so that's 1, 2, 3, 4, and then you go up to, how far down? That was minus 2, right? So it's 1, 2, 3, 4, 5, 6. Go up here, 4, 6, and put a little dot right there. And this is going to be a minimum. It'll be concave up. So I'll just draw something in like this temporarily. And then we think about these asymptotes, right? So what we want to do is we want to let this function approach these asymptotic values, right? So as it goes out to infinity, this guy's going to approach y equals x. And then we have to avoid this asymptote, so it's going to approach minus infinity. And over here we have the same kind of thing, approaching positive infinity, and also approaching the line y equals x. And so there is our rough sketch of what this graph looks like, which is rather complicated, yeah? Let me show you what the actual function does look like, and you can see that we're pretty close there with our evaluation of it. This would not be a fun thing to plot. After you put down a few points, you'd probably be confused as to what was going on. Yeah? I was going to give you the opportunity to try a simple example. But we've kind of run long on our time, so maybe we will just save that for the homework, unless you really wanted to see me do a simple example.
Sure.
Okay. I like the enthusiasm. Not in the slightest. Oh, come on. So I'll give you the opportunity to do it. So take a crack at graphing or sketching the graph of f of x equals x cubed minus x squared minus 6x using the 7 steps that I laid out for you. Go ahead and pause the video, try that at home. All right, well, the domain is easy. It's all the reals. There are no holes anywhere that we need to worry about. What about the evenness and oddness? Look at the symmetry of it, right? Is it even or is it odd? Well, we can try, what does f of minus x equal? It's going to be minus x cubed minus x squared plus 6x, which is because the squared term here, right, didn't change sign. It's not equal to minus f of x. So it's neither even nor odd. And by the way, that usually tells us something about a graph, right? When we're thinking of a graph, it could be, perfectly even. Maybe it did something like that, right? But if you simply offset the axes a little bit, right, such that you have your y-axis going through here, now it's no longer odd, right? Before it was odd because it was symmetrical. Now it's not, okay? So a lot of times that's what we have going on. So neither even nor odd. What about the x-intercepts? Well, we have to factor this, so that would be x times x squared minus x minus 6, which we're going to have to factor this, and that's going to give me x times 3 minus 2 is, so this is going to be x plus 3 times x minus 2. Oh, I got signs wrong. X minus 3, x plus 2. So in this case, when you see something whose factors add in a way that'll make this work, you can just do the quick factorization, right? So minus 3 plus 2 is minus 1, and minus 3 times plus 2 is negative 6, right? So you do quick factor on that. But you could have done complete the square or quadratic equation, that's fine. So it looks like we've got, where is this equal to 0, right? Because remember, the x-intercepts occur when f of x equals 0. So we've got that at x equals 0, x equals 3, and x equals minus 2. Y-intercepts are where f of 0 and that will give me 0. So I have a 0, 0, which we already had in there anyways. So let's go ahead and put up a coordinate system over here. We've got at x equals 0, it's 0. At x equals 3, well, it's an x, so it's going to be 0. So 1, 2, 3, minus 1, minus 2, minus 3. So x equals 1, 2, 3, it's 0. So there's an x-intercept, and also at x equals minus 2. Okay, so now that I've got those points drawn, I'm just going to erase this. There are no asymptotes at all, right? This thing just goes off to plus and minus infinity as x goes to plus and minus infinity. Now we need to evaluate the derivative. Let's just evaluate the derivative of this, right? So f prime of x is going to be 3x squared minus 2x minus 6. And we want to know where this is equal to 0 to find any critical points. So we want to know f prime of x equals 0. That means we're going to have x squared minus 2/3 x minus 2 equals 0. So we'll get x squared minus 2/3 x plus minus 1/3 squared, just taking half of the value in front of the x coefficient, right? Or taking half of the x coefficient, minus 1 minus 1/3 squared minus 2. So this will give me x minus 1/3 squared minus 1 over 9 minus 2, but that'll be 18 over 9. So that's going to be minus 19 over 9, which means it's equal to that. So when I take I'll get x equals 1/3 plus or minus 1/3 times the square root of 19. Not pretty for critical points. So that obviously has two values. So if I punch that into my calculator, I do 1/3 plus 1/3 times the square root of 19. What do I get? That'll give me 1.79. Just going to go over the decimals here rather than keeping all these weird roots around. And if I evaluate it on 1/3 minus 1/3 square root of 19, I'll get minus 1.12. Okay, so those are critical points. So we want to look at what does f of x look like, f prime of x. Minus infinity, we'll have a critical point at minus 1.12, where our derivative will be 0. We have another one at 1.79, where it'll be 0, and we'll go out to plus infinity. So if I do plug in, so I can use test values along the way here. So we could do like f prime of minus 2. Where's my f prime? Here we are. F prime of minus 2. Let's put minus 2 in here. That's going to be 3 times 4 is 12 minus, will be plus 4 minus 6. So this is going to be 6 plus 4, which is positive. So we get positive values in here. And then if we look at between minus 1.12 and 1.79, we could pick, for example, we may as well pick 0. That's an easy one, right? F prime of 0, that's in between these two values. What do we get? Where did we go? There we are. We're going to get minus 6, right? So that's negative. And then we pick values that are farther out than 1.79. We could pick f prime of 2, for example. So putting in 2, we'll get, that's 3 times 2 squared. It's 12 again. Minus 4. Minus 6, that's minus 10. 12 minus 10 is positive, so we're positive again. Yeah? So what does that mean? We've got positive slope, negative slope. So this is likely a maximum, and this is likely a local minimum. Yes?
Yeah.
Finally, we want to take the second derivative. Let's just see if there's any inflection points. So second derivative would be equal to, it's going to be 6x minus 2. Which means that at x equals 1 over 3, we have a possible inflection point. Okay, so we have to test it at 1/3, where we know it's equal to 0. What does it look like to the left of 1/3? Well, if we picked 0, that's negative. So we have negative values. And now we'll pick a value that's greater than 1/3, let's say 1. So 6 times 1 is 6, minus 2 is 4, so that's positive. So we see that this is, in fact, an inflection point because it changed the concavity here, right? It went from negative to positive. Yeah? So we do have an inflection point at x equals 1/3. So just circle things that are important here, and we'll try to put it all on the graph. Let's evaluate these critical points. So f, remember f, not f prime, of 1.79. If we plug it into this equation, let me just look and see what we get, because I'm not going to calculate that on the fly. we're going to get minus 8.21. And if I evaluate at the other critical point, minus 1.12, I'll get 4.06. So it's looking, it's kind of confirming what we saw, right? We do see, what appears to be a maximum and a minimum for these two critical points. Oh, the inflection point. Let's look at what is f at 1/3. And that's going to be what? Minus 2.07. Okay, so I put these on the graph here. So 1/3, that's like right in here, and it goes down to minus 2. I didn't put any 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So at 1/3, we're at minus 2. So we'll go down right about here. That's where our inflection point is going to be. At minus 1.12, we're going to be at 4.06. So go 1, 2, 3, 4. We'll go up here. We'll put it about there. And remember, that's going to be a maximum, right? At the max. So we're going to put some kind of curvy on that. And then at 1.79, that's almost 2, we're going to be at minus 8.21. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. We're way down here. So at, where do you go? 1.79, so put it like here, up here, I think. Okay, so now we can connect all this up, right? So we're going to pass through this point. Here's the inflection point. We turn around, back up through here. So this is the point where the slope changes from, where the concavity goes from concave down to concave up. And that's just going to go out to minus infinity and infinity there. So that's our, I'm not a great sketcher, by the way, but that's the sketch of the graph. And let's see, what does the graph actually look like? Well, pretty similar, right?
Yeah.
Yeah. Yeah. Looks good to me. That is, I think this is the second application of derivatives lecture that we've had. The first one was the second part of the implicit differentiation. We talked about related rates problems. So today we've talked about graph sketching, but also we've learned how to find maximal and minimal values for functions using the first derivative test and the second derivative test. That's going to come in really handy, okay? And so next we'll talk about optimization. What does it mean to optimize something, right? You want to maximize profits, right? Or minimize costs. These are optimization problems, you see?
Yeah.
So probably 2 lectures on optimization. One of them may be specifically on, business calculus stuff that kind of requires its own special terminology. So we'll definitely have one on business calculus, one on just general optimization, and then I'll have one more lecture that covers a variety of things that's useful from calculus in the sciences. So it looks like maybe 3 more application lectures, maybe 4. Okay, that's it. I'll see you next time.